All right, so last time we had class, we had finished up 8.5 part 2. We had started looking at dot product. Okay, we went through all this, and the formula for a dot product is basically you take the x components, multiply them together, take the y components, multiply them together, and add them up. So the dot product is a number. We didn't really do anything with that number. Today I'll show you what that number is used for. Alright, so we went through dot product. I think we had talked about this. Did we mention the dot product is distributive?
That's where we ended.
That's where we ended. So the dot product, you can use a distributive property with it, just like regular numbers. Alright, so the main thing that we use the dot product for is finding the angle that two vectors make. And when I talk about finding the angle, technically there's two. There's this one on the inside, and there's that one on the outside. We're finding the one on the inside, okay, the one that's less than 180. So the proof of this formula comes from the law of cosines. Okay, in the other class we went through it. I think it's about 5 to 7 minutes, so it's not an awful proof, but if we can say 5 or 7 minutes today, that's pretty good. But the idea is just to kind of give you a rough kind of thought about it. Actually, I think I have it on the next page. So if we were going to go through the proof, that's the idea. We're finding the angle between those two vectors. We start out by adding a third vector, which makes that into a triangle. Right? And then what we do is we use law of cosines on that. Because if you know all these coordinates, you could easily use the distance formula, and you could find the length of u, the length of v, and the length of the thing in black. So if you knew all the sides, that would be like having a side-side-side triangle, and you use law of cosines to find the angle. That's basically what this formula is. So every time you use this, you're really doing law of cosines. But a lot of stuff cancels out, and it kind of condenses down to that. Okay. All right, so let's look at these two vectors and find the angle between them. I'll do a quick sketch just so we can get an idea of what it should be. So we've got right 4, down 3. Okay, so that's vector u, and then right 2, up 5. Right 2, up 5. Okay, so if I look at those two vectors, to me it's almost 90, maybe a little more than 90. Could be 100, right around there. Okay, so let's go through and find the angle and see what we got. Okay, so the formula says you find the dot product and then divide by the product of the magnitude. So there's 3 things you got to find. So let's start with the dot product. All right. All right, so dot product. Okay, Shauna, can you tell me the calculation that I'll do for the dot product?
4 times 2
Yep.
plus negative 3 times 4.
Alright, so we get 8 minus 15, which gives me a dot product of negative 7. Okay, so that's the first thing I need, dot product. The next thing I need is magnitude of u. Okay, so I'll go through this one and then I'll ask someone how to do magnitude v. So we square each component, add them up and take the square root. So we get 16 plus negative 3 squared is 9. 16 plus 9 gives me 25. And the square root is 5. Okay, so now we've got the second thing, the magnitude of u. And the last thing, magnitude of v. I'm trying to get some more space. There we go. All right. Can someone give me the calculation to find the magnitude of v? Yeah, Sean?
Square root of 4 plus 25, which equals the square root of 20.
Square root of 4, so 2 squared is 4. 5 squared is 25. Square root of 29. Okay, now we've got all three pieces of information. Fill them into that formula right there. Dot product over the product of the magnitudes equals the cosine of your angle. So, dot product, -7, over the product of the magnitudes equals the cosine of the angle, but I don't want cosine, I just want the angle. So how do I get rid of cosine? Yep. I'm going to take the arc cosine or inverse cosine of each side. And now at this point, we need a calculator. So the inverse cosine, I'll change to degrees in a minute, of -7 divided by 5 square root 29. As far as parentheses, you know what, I should probably put parentheses around this denominator, because otherwise order of operations will always do multiplication and division as it sees it, left to right. But I want it to do the division first. So let's do it like that. So do the division first, that's the denominator, and then go from there. Okay, so that's the answer in radians, but I'd rather get it in degrees. So I said I was going to change it, and I forgot. Okay, so 105.07 degrees. Which, I mean, based on my sketch, looks reasonable. I thought it was more than 90. I thought maybe it was 100, but it's 105. And that's how you find the angle between two vectors. Any questions on that? Okay, there's two special cases that can come up. If the angle is 90, the vectors would be perpendicular. Although with vectors, there's a special word they use, and I'll tell you what that is. In the other cases, the vectors could be parallel. Okay, so we'll finish up this section looking at those two things. If two vectors are perpendicular, it means the angle is 90. But they don't use the word perpendicular. When we talk about vectors, they use the word orthogonal. So orthogonal means the same thing, perpendicular. All right, so what I'm going to do is I'm going to show you kind of a shortcut to figure out if two vectors are orthogonal or perpendicular. So I just said it a second ago, and it's the same, that this idea applies to all kinds of different line segments and rays. But if two things are perpendicular, what does that mean the angle is between them? Okay. 90. So let's take a look at what would happen if we force the angle to be 90. I want to know what would happen to the stuff over here. So I'm going to fill in a 90 right there, and then kind of work backwards and figure out what the other side would have to be. Okay, so let's do that. So if we had two vectors that were already perpendicular, the angle would be 90. On the other side, we have a dot product in the top and a product of magnitudes in the bottom. It doesn't really matter what they are. Okay, we're kind of focusing on the left-hand side. All right, let's take the cosine of 90. Okay, if you do that, the cosine of 90 is 0. So now, you would have 0 equals that fraction. What's the only way that this fraction could ever come out to 0? Which would then mean if you took the inverse cosine of 0, you would get 90. Yeah?
If the numerator is 0?
Right. The only way a fraction can equal 0 is if the numerator is 0. And what's in the numerator of that fraction? Yeah?
The dot product.
The dot product. So if the dot product is 0, that causes the whole fraction to be 0, which means if you have a fraction equal to 0 and you take the inverse cosine of the left side, you would get 90 degrees as the answer. All right. So any questions on that idea? If the dot product is 0, it doesn't matter about anything else. The whole thing is equal to 0, and the inverse cosine of 0 is 90. Unfortunately, with parallel, there's not quite as nice of a shortcut, but we'll get to that in a second. Okay, so this is basically just a yes/no question. Are these vectors perpendicular? If they're not, I don't care what the angle is. All I want to know, are they perpendicular? Yes or no? All right, so Leo, what did we just say? The only thing you really need to know to figure out if they're perpendicular is
if the dot product is 0.
right, all you need is the dot product. And then you have to know, does it come out to 0? And that'll answer the question. Okay, so the dot product is 2 times 1 plus 1 times 2. So the dot product is 4. Megan, are those vectors perpendicular? No. They're not perpendicular. Because now you've got 4 in the top of the fraction. But for them to be perpendicular, the fraction has to come out to 0. Well, if you have a 4 in the top of a fraction, I don't care what you divide by. It's never 0. Even 4 divided by 1,000,000,000. It's not 0. Okay? So there's no way these could be perpendicular. But what could you change to make them perpendicular? You could only change one thing. Jane?
You could add a negative to one of the 2's.
Yeah, you could make one of the 2's negative or make the I or the J negative. Just put a negative in anywhere. And it would automatically give you -2 plus 2. And then they would be perpendicular. Okay. Any questions on that? Right, so that's perpendicular. Now we're going to look at parallel. Well, there's 2 situations for parallel. Those 2 vectors are parallel, or you could think of them as moved off each other if you want. The angle between them would be 0. Think of them as like on top of each other. They're both pointing the same way. So that's one situation for parallel. So is that. What's the angle between those 2 vectors? Yeah?
180.
180. Well, if they started at the same spot, going around, that's 180 degrees. So let's do the same thing we just did. Let's force the angle to be 0 and see what happens to the right-hand side. So if these vectors were parallel, one possibility is the angle is 0. The cosine of 0 is 1. So if the vectors are parallel in this case, this fraction would have to come out to 1. How does a fraction come out to 1? Yep. Right, the numerator and denominator, so you need to know both. So it takes a little longer, but if they come out the same, it would equal 1, which would mean the angle between them is 0 degrees, if you took the inverse cosine of 1. Okay, the other situation you could have is something like this. The angle could be 180. If the angle between them is 180, that fraction will come out to -1. That's the cosine of 180. How does that fraction come out to -1? Yeah.
You have the same number top and bottom, but one of them is negative.
Yeah. So basically, they're opposites. Okay. Same number, except one's positive and one's negative. So if your numerator came out to, say, 12, and your denominator came out to 12, that means they're parallel. But you do have to find both the top and the bottom. Okay, so same kind of question we just had last time. I'm going to ask you if these 2 angles, or these 2 vectors are parallel. Okay, so we're looking for one of 2 angles. Either the angle between them is 0, which means the fraction comes out to 1, or the angle is 180, which means the fraction comes out to -1. Okay, so we've got the vectors 4i minus 5j and 20i minus 25j. We'll start out with the dot product. Okay, Abby, what am I going to multiply to get my dot product?
4 times 20
Yep.
plus -5 times -25.
Okay, so the dot product is 80 plus 125, which is 205. Okay, so we got the top. Now we need the two things in the bottom. So let's start with magnitude of V. Sam, how would I find the magnitude of V?
You take the square root of 4 squared plus 5 squared.
Square root of 4 squared plus 5 squared. So that's 16 plus 25, square root of 41. Okay, so there's the magnitude of V. And Juliette, what about the magnitude of W?
It'd be 20 squared
So 20 squared, which is 400,
plus 25 squared.
and 25 squared is 625. So that's the square root of 1025. Okay, so now we know the two things that are in the bottom. Let's see what it comes out to when we multiply them together. Okay, so at this point, what I'm really finding is this. I've got the dot product, that's 205. I'm going to calculate what this is. If it comes out to 205, then my fraction would come out to 1. If it comes out to -205, then my fraction would come out to -1. Well, it can't be -205. We're only dealing with positive numbers. Square root of 41 is a length. Square root of 1025 is a length. Positive numbers. Okay, so they've got to come out to 205 for this to be parallel. All right, so the square root of 41 times square root 1025. And it comes out to 205. Okay, if you got that and you still didn't remember the trick about them coming out the same, you would now have the cosine of theta equals 1. And if you take the inverse cosine of each side, you get an angle of 0 degrees, which is one of the two cases for being parallel. Okay, so the answer here is yes, these are parallel. Okay, any questions on that? All right. All right, so we'll look at the word problem, and then that'll be it for this section. So I'll sketch it out. You don't really need to, but it might help a little bit. And we're going to be looking at an airplane that's flying at a certain speed. The wind is going to be blowing, and I want to know how that's going to affect the plane. Could speed the plane up, it could slow it down, depending on the direction of the wind. And it might also blow it off course a little bit, depending, again, on the direction. The two things we just have to make sure we understand first is the difference between the airspeed of a plane and the ground speed. The airspeed is how fast the air is moving over the surface of the plane. The ground speed is if somebody pointed a radar gun at the plane from the ground, the radar gun could reach it and tell you how fast it's going. That's the ground speed. And if you're thinking, well, aren't they the same? They don't have to be, depends. Imagine there was a day where there was no wind outside. Okay? If somebody's standing perfectly still, they don't feel any breeze. If you drive down the highway and your speedometer says 50, and you put your hand out the window, the wind is going to hit your hand at 50. Now let's say on a different day, somebody that's standing perfectly still feels a breeze of 20 miles an hour. Not moving at all. They feel 20-mile-an-hour wind. And let's say you drive your car straight into that wind. So the wind is like hitting your windshield. Well, if you stick your hand out the window now, if your speedometer said 50, that's not how fast the wind would hit your hand, because the wind was blowing 20 right at your car. And now you're driving into it at 50. So really the wind would hit your hand at 70. Does that make sense? Okay. So that's the difference between airspeed and ground speed. So this plane is maintaining an airspeed of 500 miles an hour south. Our goal is we have to turn that into a vector. So south has an angle, which we need to know, and it has a magnitude. Those are the two things you need to write a velocity vector. We already know the magnitude. We have to figure out the angle for south. Okay, the wind or the jet stream has a magnitude of 80 miles an hour, and the direction is northeast. Well, again, we have to turn northeast into an angle. If we can't turn it into an angle, we can't do this. Okay, so we got to know the compass a little bit. So what I want to do is just find the actual speed. Don't worry about the direction, because we're not going to have enough time to do that. But I just want to know the actual speed of the plane relative to the ground. So according to the pilot, if they look at their airspeed indicator, it's going to say they're going 500. But somebody with a radar gun on the ground tracking the plane is not going to be going 500. If a plane is trying to go south and the wind is blowing northeast, is the wind going to speed the plane up or slow it down?
Slow it down.
It's going to slow it down. The plane wants to go south, the wind is blowing in a northerly direction. Okay. Another thing you have to be careful of when they word this kind of problem, they can either tell you the direction the wind is blowing, like I did. The velocity of the jet stream is in a northeast direction. Or they can say the wind is coming from the southwest. Saying it's blowing from the southwest is the same as it's going towards the northeast. Okay? So keep that in mind. All right. So just kind of a quick sketch of what's going to happen, not to scale, but that's the velocity vector for the plane. The plane wants to go south. The wind, V sub W, wants to blow the plane northeast. To figure out the actual direction of the plane, all I have to do is take this and just temporarily put it right there. And what I just did was add the wind and the plane together visually. And I got the vector in black. So what's in black is what's actually going to happen. Notice the black arrow is a little shorter because it's not going to go as fast. And it's also not going south anymore. It's blowing the plane off course. Okay? And that's not to scale, but that's the idea. So the way I got V sub A was I took the vector for the plane, the vector for the wind, and I combined them together. That's the big idea for this problem. You have to do that. But you have to turn this all into numbers. Any questions on how I got that equation? Okay, so now let's find out what each of these vectors are. The vector for the plane. So a velocity vector is the magnitude times the cosine of the angle plus sine of the angle. So we've already got the magnitude. The plane is going 500 miles an hour. Now I need cosine of my angle. The plane is going south. Okay, if you're not familiar with the direction, there you go. What angle would be south? What's the angle that we would always put where S is? Yep.
270.
270. Yep. So cosine 270 plus sine 270. I put an I with the first one because that's the horizontal. I put a J with the second one because that's the vertical. Okay, let's do that out. So what I'm finding right here, the I is the left-right component of the airplane speed. Well, there isn't now. The plane is traveling perfectly south. There is no left-right to the speed of the plane. All the speed is in the south direction. Okay? So that's why the first part is 0. So the second part is 500 sine 270, and we get negative 500j. All the speed is on the vertical. Okay? So really what I should do is just put minus. And there's the velocity vector for the plane. Okay? Any question on how I got that? Okay, anyone think they can set up the cosine sine expression to find the vector for the wind? Oh, Gracie?
Would be 80.
Yep, so she started with the magnitude, that's perfect. Now the only thing she needs is the angle.
And then would it be 45?
Yes, it's blowing exactly north and east. That's a 45-degree angle. Now, because it's blowing exactly at a 45-degree angle, the east component and the north component are gonna, how would they compare to each other? Yeah, they're gonna be the same. So once I find one, I really don't need to do the other. So they're both going to be 56.57. So 56.57i plus 56.57j. Now I've represented everything in the problem as velocity vectors. And I can now combine them together to find the formula for the vector in black, okay, V sub A. Okay, so V sub A is going to be, actually I won't even number them 1 and 2, I'll just say V sub P plus V sub W. V sub P doesn't have an I component to it, so when you combine it with V sub W, it's just 56.57i. Plus, actually it's going to end up being minus, negative 500 plus 56.57. So negative 500 plus 56.57. So negative 443.43. All right, so now we have a vector that represents the combined effect of the wind and the plane. Now, all I want to find here is the speed. The speed is part of V sub A. What would I have to find with V sub A to get the speed of the plane? Because that's its velocity vector, but I want to pull the speed out of that. So this, what's another word for the speed?
You have to find the magnitude.
The magnitude. That's what I need. So the magnitude of that would give you the speed of the plane. And now from here, it's just like using your Pythagorean theorem. So it's the square root of 56.57 squared plus 443.43 squared. And if you're saying, well, wait, you forgot the negative doesn't matter because it's going to cancel out. So the speed of the plane is 447.02 miles per hour. That would be the speed, if somebody had like a radar gun and they could track the plane, that's how fast it would be moving. Or better yet, maybe a satellite, if a satellite could track the plane. Okay. It's a little bit of work because you got to find a couple vectors and add them up. But that's the toughest question we really do with vectors all week. Any questions on any part of that? Yeah.
So what did you do with all of them, like to get the miles per hour?
Miles per hour? So I plugged everything in to that formula, the square root of 56.57 squared plus 443 squared.
Oh.
That's the formula for the magnitude. Any other questions? All right. So the homework for this section, it's the same problems you already did. 7 to 17 odd. I think you already did part A. So now do parts B and C. So A was finding the dot product. B is finding the angle, which you need part A for. And then part C is answering the question, are the vectors parallel, perpendicular, or neither? And then 25 is, that's an airplane question. Okay, so any questions on what the assignment is for part 3? All right, last section. So part 4 is pretty much a review of everything we did in 2D. Okay, there's no word problems. We don't do any word problems in this section. It's all stuff we did in 2D, now just extending it to 3D. The only thing that's a little different in 3D, if we get to it, is the cross product. Okay, cross product is something I could not teach you in 2D because it doesn't exist. So first we'll go over all the stuff we did in 2D, extending to 3D, and then we'll go from there and see if we get to cross product. All right, so first of all, sketching in 3D is kind of tough, so we're not going to really do any sketching at all. The only thing I'm going to explain is how the axes work. So if you think of this as like a box, the XY plane is where we did all our stuff before. It's like the bottom of that box. Well, the z-axis is allowing us to come up off the bottom of the box. So if the table is the xy plane, the z-axis is coming off the table. That's what that's trying to show. And the coordinate system is what we call right-handed. So what that means is if your index finger points in the direction of the positive x, your middle finger points in the direction of the positive y, your thumb will point in the direction of z. So as long as you know the directions of x and y, your thumb will tell you which way z goes. Now it's right-handed because if you do that with your left hand, and you line up the x-axis, your middle fingers are the y-axis, the z-axis points opposite ways. If you use your left hand, you get one way, right hand, opposite. We use the right-handed system. That's just how this works. All right, so any questions on the axes? So the only formula we're going to look at today that doesn't involve vectors is this one. Finding the distance between 2 points in 3D. So what I'll do for every formula is I'll put something like recall. I'll show you the 2D version, which this is going to just be the distance formula. If you want to write it, you can. But we're really going to focus on the 3D stuff. So in 2D, it's the difference in the x's squared plus the difference in the y's squared. It's just the Pythagorean theorem. Now in 3D, your coordinates have to turn into 3D coordinates. So you could call these coordinates, or you could call them ordered triples. You don't want to call them an ordered pair. Ordered pair is 2. That's 2D. So the formula kind of starts out the same, but does anyone have a guess what I'm going to put on the end of that to turn this distance formula that's 2-dimensional to 3-dimensional? Yeah?
Plus z subscript 2 minus z subscript 1 squared.
Yeah, we're going to put plus z sub 2 minus z sub 1 squared. And that's pretty much how everything we do up until the cross product is extended to 3D. Just look at the pattern you had before and do it one more time for the z's. Okay? Just follow whatever the pattern was. Okay, so let's find the distance between these 2 points in 3D. So P1 is -132, and P2 is 4, -2, 5. Does everybody have up to the formula? Okay, so I'll leave the formula there. And let's find the distance. All right, so Trevor, can you tell me the first 2 things that I would subtract?
4 minus -1.
So 4 minus -1, and we square it, plus, Tessa, can you give me the next 2? -2 minus 3, squared. And Caleb, last 2?
5 minus 2 squared.
5 minus 2 squared. Okay, so we do that out. We're going to get 4 minus -1 is 5 squared. -2 minus 3 is -5 squared. And 5 minus 2 is 3 squared. So the distance between those 2 points is the square root of 59. Just like you would in 2D, if you can reduce that, go ahead. If not, just leave it. Questions on that?
But what does the distance actually mean? Because if you're finding a distance between 3 points, wouldn't that make a triangle between the 3 points? Like,
3 points or just 2 points?
oh, okay, I was thinking about it.
Yeah. So the points are 3-dimensional, but there's still just 2 of them. Like 1 here, 1 here. So it's just a 3-dimensional distance. Well, it's a distance between 2 3D points. Okay, any questions on that? Okay, so every other formula today is going to be with vectors. So in 2D, okay, I'm going to get away from saying horizontal and vertical component, because in 3D that doesn't always make as much sense depending on how things are tilted. But in 2D you had an x-axis component and a y-axis component. A tells you how far to go and what way to go on the x-axis. B tells you how far to go and which way on the y. Well, in 3D we have to extend it so we have one more unit vector. So I is a unit vector that points 1 unit in the positive x direction. J is a unit vector that points 1 unit in the positive y. And K is a unit vector that points 1 unit in the positive z. And now using multiples of I, J, and K, you can stack them together and move anywhere you need to in the plane. So you can move left and right, up and down, and forward and back, stacking together ij's and k's. If you wanted to write it as an algebraic vector with the brackets, you just write the components. X-axis, y-axis, and z-axis components. Does anybody remember the name we give to a vector that has its initial point at the origin? Yep. So unit vector is when it has a magnitude of 1. But this is something a little different, when the initial point is at the origin. It was the last thing we did in 8.5 part 2. Yeah? No, that's what Megan says. Not a unit vector. Begins with a P. Yep. Yes, position vector. I wrote down the exact same definition again. You should hopefully already have that in your notes in 8.5 part 2. The definition doesn't change in 3D. If the initial point's at the origin, it's still called a position vector. Okay, so that'll be our first formula for vectors in 3D. I'm going to show you the formula to find a position vector. Okay, just like the last one, I'll start out in 2D, and then I'm going to ask you, what would you add to the formula to make it 3D? So there's the formula from our first day of class at Monday. Yeah, Monday. Difference in the x's, comma, difference in the y's. It's important the order you do the difference in. Always do terminal minus initial. So now in 3D, your initial point will have a z part to the coordinate, and so will the terminal point. Okay. Anyone think they can tell me what I'm going to add to my position vector formula in 2D to turn it into 3D?
Z2 minus Z1.
We're just going to have to subtract the z components with everything else. So z, we have difference in the x's, comma, difference in the y's, comma, difference in the z's. Always terminal minus initial. So if you're going to make a reference sheet, really, I would just write the formulas in 3D down. Because if you have to do a problem in 2D, you could just pretend like the z's are what number? Yeah.
0.
Just pretend that the z's are 0 if you want to use the 3D version. We're actually doing 3D, so the z's are not going to be 0 today. Okay, so let's find the position vector. So difference in the x's, terminal minus initial, difference in the y's, terminal minus initial, difference in the z's. And we need to write that up. 5, 4, -1. That's the position vector. So what that really means is its directions. If you start at the origin, go 5 units along the positive x, go 4 units along the positive y, go 1 unit on the negative z-axis, and you will get to the terminal point. Any questions on finding a position vector? If you want it, you could also write it 5i plus 4k minus j. Okay, you should be comfortable with both. Any other questions on that?
Wouldn't the 4 be with J?
IJK. Yes, thank you. It's always alphabetical order. I'm not sure why I shouldn't have done that. All right. So now the next thing we're going to look at is adding, subtracting, scaling from the magnitude. But we're not going to do any of it with a sketch, just a formula. So here's two vectors. Both vectors have x, y, and z components to them. And if this was a 2D problem and we wanted to add these up, we'd add the x's, comma, add the y's, and you'd be done. Now in 3D, one extra step. Add the z's. Okay, and I kind of did addition and subtraction as the same formula. With subtraction, subtract the x's, subtract the y's, subtract the z's. Okay, next thing we're going to look at is when you put a number in front of a vector. Does anybody remember what you call this number? We don't really call it a number because it can change the length of it. Yep.
It's a scale factor, was it?
A scalar, yep. We call it a scalar. So three things can happen. It can make the vector longer, shorter, or flip the direction. In 2D, okay, to scale a vector, you multiply the x component by your scalar and the y component by your scalar. Well, now you just have to distribute it out one more time to the z. Okay, so hopefully you're seeing it really when you do it in 3D, nothing changes. It's just there's an extra step for each formula. Okay, and magnitude. There's your formula to find the magnitude of a vector in 2D. What do you think I'm going to put on the end of that to turn this into 3D? Tell me.
Z1 squared.
Plus z1 squared. Yep. Okay, so we'll go through an example of finding each one of those. Maybe I'll skip subtraction. We'll just do addition, a scalar product, and a magnitude. Okay, any questions on the formulas before we try some examples? All right. So here's our two vectors. Let's add them up first. Okay, so just think of it as combining like terms. The i's, the j's, and the k's. Okay, so Tanya, if I add those vectors up, what would I get?
As like a formula?
Just the final answer when I add those up.
Oh, 5, -1, 3.
Yep, and we'll write it like that in a second. Can you tell me first with ij's and k's in there, and then I'll write it that way?
-1j, 3k.
So 5i minus j plus 3k. Okay, the way I said it, minus j, if you want to put minus 1j, that's fine. Or the way that she said it first was also correct. 5, -1, 3. Okay, any questions on how we got that? Okay, so there's a sum. Let's find the magnitude of v. Shauna, can you tell me how I would set that up?
You have to do the square root of 2 squared, which is 4. 3 squared, which is 9. And -2 squared, which is 4.
Okay, like that?
And then add.
And then add them. Yeah. So we're going to add add those up. So the magnitude of that is going to be square root of 17. Any question on part B? Okay, part C is a scalar. 3W. I want to find 3W. So I'm just going to go back up so we can see it. Gracie, can you tell me what, if I do the scalar product, 3W, what I would get?
It'd be 3 times 3. Right?
Yep, you can, yeah, go ahead. You can just tell me the whole thing with I, J, and K.
II minus 12J plus 15K.
Yep, looks good. Perfect. So that's a scalar product. Any questions on that? All right. So now we're at the point just about where we left off with Monday's lesson. I'm looking at dot product and finding an angle between two vectors in 3D. All right. Actually, this time, does anyone think they can tell me what the formula is for the dot product in 3D based off how it works in 2D? It's exactly what you would expect. Yep.
X1 times X2 plus Y1 plus Y2 plus Z1.
Can you say that again? Plus?
Plus Y1 times Y2.
Yep.
And then plus Z1 times Z2.
Exactly. So you multiply your X components, plus multiply your Y components, plus multiply your Z components. And that's your dot product in 3D. All right, so now let's practice finding a dot product in 3D. So we're really just going quick, doing one example of each thing we did in 2D, now extended to 3D. Okay, so let's find the dot product between V and W. And the next thing I'm going to do is I'm going to find the angle between V and W. But if I build in finding the dot product now, we'll already have one thing done for the next step. So start with dot product. Jane, can you tell me how do I get my dot product?
Well, you would do x1 times x2,
Yep.
would be 10,
So we get 2 times 5, which would be 10. Yep.
plus, or minus 9,
Plus negative 3 times 3, so it's plus negative 9 or just minus 9.
and then plus negative 6.
And then 6 times negative 1 is negative 6. So 10 minus 9 gives me 1 minus 6. There's my dot product. And that's it. That's a 3-dimensional dot product. Questions on that? All right. So last thing we did in 2D was finding the angle between vectors. So it turns out the formula is the same. There's no change in how the formula looks. What's different is kind of the parts of the formula. In 3D, you're doing a 3-dimensional dot product, which you just did, over a magnitude calculated from a 3D vector times another magnitude calculated from a 3D vector. Before, it was a dot product from 2-dimensional vectors over magnitudes from 2-dimensional vectors. Okay, but the formula itself doesn't change. So let's find the angle between the two vectors we just had. These are the same ones. And I'm doing that just to save a little time on the dot product. So we already have the dot product here. What did the dot product come out to?
Negative 5.
Negative 5. That's the first thing. Okay. What are the other two things that I need to figure out the angle? Yeah.
The magnitude of the view and the magnitude of the
Yeah, I need the magnitudes. Is there anything I can say about the angle between the vectors right now, knowing the dot product is negative 5? Yeah.
they're not parallel or equal? Or,
I can't say that much.
They're not orthogonal.
Right, they're not orthogonal. I know that. If they were perpendicular or orthogonal, it would have come out to 0. Are they parallel? I have no idea yet. Okay. Well, I do, but at this point, we don't have enough calculations to determine that. So now let's find the two things Julianette just said. The magnitude of u, 4, 9, 36. If you add that up, you get the square root of 49, which is 7. And then 25, 9, 1. So that's the square root of 35. Okay. I can tell you they're not parallel because I know the square root of 35 is about 6. And 6 times 7 is roughly 42. And that's not even close to -5. So the top and bottom aren't going to come out the same. So let's see what they come out to. Cosine of my angle, dot product over the product of the magnitudes. And to finish that up, what would be my last step? Yep.
You take the inverse cosine.
Take the inverse cosine. Inverse cosine. -5 divided by, let's see, 7 square roots of 35. Okay, so we get an angle of 96.9 degrees. Okay, any questions on that? All right, so last thing I'm going to show you is something we did not do in 2D. Okay, it's called the cross product. The reason I didn't show it to you in 2D is because you can't do it. Cross product only works in 3D. And it's a second way to multiply vectors together. And it's written with this symbol, the little cross, V cross W. So now, if you gave me two vectors in 3D and said multiply, I would have to ask you to be more specific. Do you want to do it as a dot product or a cross product? Now, if you gave me two vectors in 2D and said to multiply them, it's clear what you want me to do really because I can't do cross product in 2D. I only have one option, dot product. And there's different applications in physics and geometry with cross products. We're not getting into applications. I'm strictly going to show you how to find a cross product, and that's it. Okay, the way I'm going to show you how to find a cross product is called Sarris's rule. The disadvantage to this is you're not really going to understand why or how it's working. You will be able to find a cross product between two vectors that are 3D, but if I gave you vectors that were 4D and said to find a cross product, this wouldn't help you at all. You'd be completely lost. This is kind of like I'm giving you a fish rather than teaching you how to fish. So it's great for this one thing, but it doesn't really help you in general to do anything else. But the reason I'm doing that is because to find cross products, you have to know how to find determinants. So this is kind of a way around that. It'll automatically find what you need without you even knowing you're doing it. Okay? But in general, to find cross products, you use what are called determinants, which I don't really want to get into that. That's why we're going to use Sarris's rule. So you would start with two vectors. Okay? When we do a real problem, they would be something like that. But for now, I'll just represent the components as A, B's, and C's. And Sarris's rule is a very visual type of thing. Okay, we're gonna make a table, or what we actually call it is a matrix. Does anybody remember working with matrices in algebra 1 or 2, probably 2. Don't be confused by matrix. Matrix is just a fancy way of saying you're going to line things up in rows and columns. If you do any programming on a computer, we call it an array. Same idea. So we're going to put in this matrix, no matter what the problem is, the first row is always ijk. The second row is going to be the coefficients, a1, b1, c1. We put those numbers right there. And the third row would be the coefficients a2, b2, c2. Okay, so that's what you start with. Any questions on that? The next thing we want to do is take these two columns. We're going to leave them where they are, but we're going to make an extra copy of them on the right. So you're going to copy columns 1 and 2 to the right of column 3. So copy columns 1 and 2 to the right of column 3. So now what you'll have is another I, A1, A2, J, B1, B2. Okay, and I have something circled. You can ignore the stuff that's circled on diagonals right now. But all I did was circle all the diagonals. I'll show you why in a second. So after creating the copies of the columns, you should have something like that. Now, what works out kind of nice here is to find what you need. All you have to do is look at the diagonals. There's 6 of them. If you don't have different colors, it might make more sense to label the diagonals 1 through 6. That might be easier. 3 of the diagonals go down and to the right. 3 of the diagonals go up and to the right. We're going to be finding products. So what we're going to do is we're going to take everything that's in red 1 and multiply it together. So take everything that's in red 1, multiply it together. Plus, take everything in red 2 and multiply that together. Plus, take everything in red 3 and multiply that together. So the 3 diagonals that go down and to the right, you multiply and you add them all up. Now it looks confusing, but 10 of these letters are going to turn into numbers when we do a problem. The only thing that won't be numbers are the I, J, K, I, J row. Everything else is numbers. Okay, now the blue diagonals, we're going to multiply together everything that's on the blue 1, but we're going to subtract it. We're going to multiply blue 2, and we're going to subtract it, and then we're going to multiply blue 3 and subtract it. Okay, so your first parenthesis will be a number with K, the second one will be a number with I, the third one, a number with J. Blue 1 will be a number in front of a K, blue 2, number in front of I, blue 3, a number with J. And then we'll have some like terms to combine. And what you're really doing without knowing it is you're working with determinants. You just don't need to know that you're really doing that. Okay, so we'll do 2 examples. I'm going to give you vectors, and we'll find the cross product one way, and then we'll switch them and find the cross product the other way, and see what happens. Does everyone have the formula? So here's our 2 vectors. Find V cross W. Okay, Jane, what do I start with in the top row for my 3x3 matrix?
You use the I, J, K.
I, J, Okay, so we start with ijk. What's going to go right below ijk?
2, 3.
2, 3, 5. And what's going to go below that? Yep.
1, 2, 3.
1, 2, 3. Now I'm going to take columns 1 and 2, copy them over. I, J, 2, 3, 1, 2. Okay. Multiply all the columns that go down and to the right. What's I times 3 times 3? 9i. J, 5, 1. 5j. K, 2, 2. 4k. Now the part you have to remember is you're subtracting the other ones. K, 3, 1. So subtract the 3k. I, 5, 2. So got minus 10i. And then j, 2, 3. Minus 6j. So combine your like terms, and that's your answer. 9i minus 10i. 5j minus 6j. And 4k minus 3k. That is the cross product. And notice the kind of answer that we got. It's a vector. So when you do a cross product, the answer is a vector. Okay. So we'll finish up with W cross V, and I want you to see what happens. Usually, when you have multiplication, does the order matter? No. Usually you can switch the order, you get the same thing. Well, let's see what happens here. So we've got I, J, K. And what's going to be the difference with how I set this up from what I had up above to what I'm going to put now? How is it going to change to show W cross V instead of V cross W?
The W is going to be the second row.
Yeah.
The last one.
So we're going to put the 1, 2, 3, and then the 2, 3, 5. Copy over the columns. And now we'll multiply and see what we get. I25 would give me 10i. J32. 6j. K13. 3k. Now the next ones, we want to make sure we remember to subtract. K22. Minus 4k. I33. And the last one, J15 minus 5j. Okay. 10i minus 9i. I. 6j minus 5j. J. 3k minus 4k minus k. Did we get the same answer? No. But what's the connection between the two answers?
They're opposites.
The direction is opposite. So these two vectors have the same magnitude, because if you found the magnitude, it would be the square root of 1 plus 1 plus 1. So they both have a magnitude square root 3, but they point in opposite directions. And the last thing, we're not going to have time to go through it, I'm just going to tell you it, is if you found the angle between the cross product and the original vectors, it's perpendicular. So that's what the cross product does. It creates a vector perpendicular to the original 2. And I'll just put that in the video so it's there. The vector created from the cross product is perpendicular to the original ones you started with. Okay, so that's cross product. All right, so the homework for the 3D stuff. It's the last page in your packet, very backside. 15, 17, 29 to 35 odd. 41, 43, 51. And then there's no cross product problems in the packet, so I just made up one. So find V cross W. And technically, once you know V cross W, you automatically know W cross V. Okay, based on what we just said. Okay, so this will be due on, let's see, so April, next time I see you is April 9th. That's a Monday. Okay, and that's for period 2-3. If you're watching this in period 5-6, this is due tomorrow, and we have our test tomorrow as well for period 5-6, not for you guys.